say also? 25 seconds now, Michael? Okay. So a very good evening to everyone who is watching our ASP's airport session for September. Okay. So my name is Dr. Chong from the Astro Society of Penang. So this society is based in Penang, which is on a small island in the northwestern corner of the peninsula of Malaysia. So we are south of Thailand and to the east of Indonesia and to the north of Singapore. All right. So we have this at the end of every month, Sunday, we present our airport scene the year 2020. So I'll just present some of our what they call presenters for tonight. Our Miss Chiu Boon Wei, okay, she's a long-time member and she's working in a multinational company in Penang. And our very young member, what they call this, Rayan Akadri, right? He's in KL and he's soon to pursue his university studies in University of Sydney under the Dal program for the school, the students, gifted school children, all right? And of course, our new presenter, Dr. Jiva Nadaraja, all right, from Ipoh, and who's a long-time amateur astronomer with a lot of experience in observational astronomy, together with handling telescope and also accessory. And watching is our Dr. Andrew Tornett. Welcome, Dr. Andrew Tornett from Lichfield Astronomy Society in Centre of England. So he's observing. All right, welcome, Andy. So we start now for this what they call September. So I will share my screen now. Wait. A bit slow. Yeah. Can you see my screen, Boon Wei?
Yes.
Wait. Wait. That's it. So basically, this is we go back again. So basically, it's lined up like that. And you see, so they have it for what they call every month. And I've been following this since the beginning, 1994. APOD appeared, and it's an amazing website. So 23 September 24 today, the Ring of Fire Sunrise Solar Eclipse. Okay, there you have it. Basically, it's a video, YouTube video, and it's taken by two amateur astronomers from Australia, Mr. Colin Lake and Mr. Jeff Sims. Okay, they actually not only astrophotographer, they actually landscape photographer, technical photographer. All right, and now basically is that the moment when the sun rose in the east, the annular solar eclipse appeared. It's on the case for 10th of May 2013. I'll give you a bit of background before we look at the video. All right, so that's it. So now you have here, you have, of course, Asia there, Malaysia's over there, and then you have Australia, New Zealand, and then you have the Central and Pacific Ocean. So basically, on 10th of May 2013, the moment the sun rose in Western Australia on the east, looking towards the east, the annular eclipse already appeared, and we'll show you the video. And because the part of annularity where you have the ring of fire will move from the west to the east. Solar eclipse always move to the west to east. Why? Because it's a shadow of the moon crossing the Earth's surface. The moon will orbit around the Earth in the anti-clockwise direction. That's why the shadow always moves from west to east, and it moves at the speed faster than the speed of sound. So the part of annularity moves west to east to the speed of sound. And here we are going to observe where in the video, and then going to cross into Northern Territory, Queensland, and will pass over to Solomon Island, and in the Central Pacific, the Kiribati Islands. All right. So we play the video now of the annular solar eclipse as observed from Western Australia. You can see the desert. Look at the eastern part. All right. 10th of May, 2013. I'll make the screen smaller. There's a kind of sound. I hope you can hear it. So now this is, so the moment the sun rose in Western Australia, already is in annually. Now this in front is the clouds. The clouds in the horizon, eastern horizon, blocking the view. But there you are, the ring of fire is up. And you observe that it's not really circular. Because the air in the eastern horizon would distort the shape of the sun. Annularity. Unfortunately, there's no green flag. There you have the ring of fire as observed from Western Australia on 10th of May 2013. And remember, recently, our Astronomical Society of Penang members, our William and Kenny, they were in Exmouth in Western Australia, 20th of April, to observe the total solar eclipse. All right? And they're already planning, Andy, please take note also, Dr. Jiva, on the, it's in 2028, 5 years from now, another total solar eclipse over Northern Territories in Australia. And our members are already planning to go there, all right? On 2028, total solar eclipse over Northern Territories in Australia. So now I pass to our next presenter. Rayan, you're on. Okay.
Thank you. Thank you, Dr. Chong. Let me see. Let me try to share my screen here. Okay. Can you see? Oh, it's loading.
Yes, I
Yes,
can
I
see
can
the
see the
screen
screen
now.
now. Okay, can you see the picture?
Great, nice picture.
It is absolutely a beautiful picture. Let me zoom out here.
Yeah.
Okay, we've got that right there. Okay, can you still see the picture?
Yes, you see.
Wonderful.
Wonderful.
Now, centuries ago, this place here, Syracuse in Sicily, was a stronghold of the Mediterranean world. Today, among other things, it's the home of astrophotographer Kevin Saragozza and the Castello Magnace, this castle here, a 13th century castle named after the Byzantine general who took control of Syracuse in 1038 AD. Now, looking down upon this historic castle is the moon, but not just any moon. It was taken at the end of August this year, and here Signor Saragozza has captured something we call a super blue moon. Now, you may be wondering, what does that mean? Well, it sort of has blue stripes, but there's nothing really super about it. Let's break down exactly what super blue moon means. Now, supermoon is just a sexy name coined by an astrologer named Richard Noel. The scientific term for this collision of phenomena, which I'll explain in a moment, is a perigee syzygy. See, it's not as vivacious as supermoon, but still, the name gives us more clues as to what's going on here. A perigee refers to when the moon reaches its closest point to Earth, a distance of about 336,000 kilometers. contrary to the 405,000 kilometers the moon reaches at its apogee, or its furthest point to Earth. Now, syzygy refers to the alignment of three celestial bodies. Conjunctions, oppositions, these are all syzygies. Now, here, the syzygy is between the Sun, Earth, and the Moon, in that order, aka a full moon. But wait, you might ask, isn't that also an eclipse? Well, you'd be right, it is. However, while the full moon happens monthly, lunar eclipses occur once, twice, thrice, sometimes never in a year. And this is because lunar eclipses require the moon to pass through the Earth's shadow, whereas full moons are simply the alignment of the three bodies, which means the moon may pass over or under the shadow of the Earth. Now, together, these form a supermoon. Basically, the moon is in its full phase and at its closest point to the Earth. To share with you a little bit of how that might look different, I have here a little image comparing the average full moon, a micromoon, which is when the moon is at its apogee, and a supermoon. You can see that it's a little bit brighter, but the size may not be too apparent. So there's this other beautiful image right here. This shows the difference in size much more clearly. This is basically what we get comparing supermoon and a micromoon. Now, supermoon can sort of happen when you have a new moon that is at the perigee, but we can't really see that, so we don't refer to it as supermoon. It's not as unique. It's not as important as this is here when we have a full moon at its perigee. Back to the image here. So that covers the supermoon part. What about the blue moon? Well, the moon definitely doesn't look blue here. So why do we call it a blue moon? Well, the definition of a blue moon has changed over the years. Originally, it referred to the third full moon in an astronomical season containing 4 full moons. Now, what's an astronomical season? It's the same spring, summer, autumn, winter seasons that we have, but the date that it starts and ends is marked by solstices and equinoxes. Astronomical summer, for example, it starts on the summer solstice on June 21st and ends on the autumn equinox on September 23rd. That's then followed by astronomical autumn, which starts on the autumn equinox and ends during the winter solstice on December 22nd, and so on. So the old definition of a blue moon was the third full moon of an astronomical season with 4 full moons. Nowadays, however, we define it much more simply. It is the second full moon in a calendar month. And usually you only get 1 full moon a month. So in the rare case that there are 2, the second is called a blue moon. In terms of the naming here, it's unlike the pink moon, because we don't quite know where the name blue moon came from. Pink moon is the first full moon in the month of April, and it's generally thought that the name comes from the pink phlox wildflowers that bloom in April. The blue moon, on the other hand, has various possible name originations. Some say it came from the phrase, the moon is blue, a 15th century saying for something that is impossible. Others say it came from a mispronunciation of the word belou, which means to betray, and was referring to how the moon was betraying the worshippers trying to predict the position of the moon. But whatever it is, the name has nothing to do with the color, but rather its rarity. And the main definition here that we refer to is the second full moon in a month. So combine these 2 things, supermoons, which supermoons, they happen about 3 to 4 times a year. The next one is actually going to be on 29th of September this year, so just 5 days from now. Combine those with the blue moons, which are much, much rarer. You get them only every 2 or 3 years. The next one is going to be 2026. Last one is 2021. But combining these 2 effects, you get the beautiful, rare astronomical event of a super blue moon. The reddish tint here is likely to do with the time it was photographed on this once-in-a-decade event. Seriously, the next super blue moon will be in 2037. That's another 14 years to wait until we see this event again. That is Blue Supermoon Beyond Syracuse by Kevin Saragotza. On to my next APOD. we have the one
Wow.
for. Ooh,
Nice.
I may have spoiled a little surprise there.
Nishimura. Wow.
Yeah, Comet Nishimura. Beautiful thing. And a lot of the images I have for my APOD today, depending on where you are in the world, have a foreground background system going on. So here, the foreground is the Carpathian mountain range of Central and Eastern Europe, specifically the part of it that borders Slovakia and Hungary. And this photograph was taken close to sunrise and was composited by astrophotographer and artist Petr Horálek, who completed his Masters of Outreach of Astrophysics in the Czech Republic's Institute of Physics in Opava, which you can see right here, Institute of Physics in Opava. Now, what do we see here? Well, Horálek has included two bright celestial objects. First, we have this very bright object here, which I initially wanted the audience to guess, but I have spoiled it way too many times. I'm sure if anyone watching has already seen what it is. It is, in fact, the planet Venus. Yes. Now, Venus is a very interesting planet. It's a hot planet, sister to Earth, overall a great celestial object. But come on, we've seen Venus so many times. So apologies to Aphrodite and her Roman counterpart, but we're going to look to the left of this image at something less ancient Greek and more modern Japanese. Comet Nishimura. Now, seeing the beautiful coma, we know this object is a comet. These tails are the result of ionization from the sun's UV rays combined with solar winds blowing them away from the sun. That's the reason why the tails always point away from the sun. But specifically, we have Comet C 2023 P1, aka Comet Nishimura, after Hideo Nishimura, the amateur astronomer responsible for the comet's discovery. Now, the naming of the comet means a lot, so let's break it down. The C refers to it being a non-periodic comet, which is a comet with an orbital period of over 200 years. Yeah, an orbit of over 200 years. 2023, that refers to its discovery year, which was this year, 2023. P refers to the half month it was discovered in. So the way these comet systems work, A refers to the first half of January, B would be the second half of January, C would be the first half of February, D would be the second half of February, and so on and so on. They don't use the letter I because it can be confused with the number 1, so the letter I is not part of that. Lastly, there is the number 1 in its name, which refers to its order of discovery. And just so that we have a picture here, this is where the name is right there, C 2023 P1, Nishimura. So if we combine that all together, what do we learn? Well, purely from the name, we learn that Comet Nishimura has an orbital period of over 200 years and was the first comet discovered in the first half of August 2023. And in fact, that's exactly what we have here. Nishimura has an inbound orbital period of 431 years. Its outbound is 406 years. And it was discovered on the 12th of August 2023, making it the first comet discovered in the month of August this year. And no, when I mentioned that orbital period, it is no exaggeration, 431 years. It's currently the closest it will be to Earth for a long time, because the next time it gets this close will be in the year 2430. So good luck seeing it then. But for now, let us just embrace and enjoy this beautiful comet that we have here, Comet Nishimura. Okay, moving on to September 18th. Ooh, that looks devilish. Let's see, what do we have here? Let's zoom in the right amount. Okay, so keeping in with the same idea of background and foreground, let's talk about what we have here. This image was photographed by photographer Maxime Villay, currently based in the Dordogne department of southwest France, between the Loire Valley and the Pyrenees mountain range. In the foreground, we have this tall, sturdy tree. Beautiful, beautiful tree right here. And then in the background, what do we have? We have perhaps an even taller, sturdy phenomenon. What is this phenomenon? Well, it's a byproduct of the storm that was passing over the Pyrenees, and it's a phenomenon known as a red sprite. Now, red sprites, they're a type of transient luminous event, or TLE, a category which includes phenomena like halos. So let's imagine something. It's a particularly stormy night, and a large horizontal lightning strike appears. Now, these strikes, which are usually positive, charge the ground positively, but also charges the top of the thunderstorm, about 13 kilometers up, with a negative charge. Above this, in the lower ionosphere, of around 100 kilometers, the charge is generally positive. So what happens? Well, this causes a surge to travel down from the top down at 10% the speed of light. And that's what we see here. That's what these red sprites are. Now, they appear red due to the same chemical properties that give aurorae their color. When atmospheric atoms get excited, they release light depending on the element. Aurorae are usually green because at that height is mostly oxygen. At the height of red sprites, which is around below 100 kilometers, it's mostly nitrogen. Now, at higher pressures, nitrogen emits blue light, but because of the low pressure at this height, the sprites end up glowing red. Now, they are by no means rare. They're not extremely rare. But they do last only a few milliseconds and only occur during heavy thunderstorms. But once you see them, they are just beautiful and actually rather big. Although they look small, they can reach lengths and widths of 50 kilometers. That is over 2 times larger than Penang Island and Penang mainland combined. So the next time a heavy thunderstorm appears at night around 200 to 300 kilometers away from you, just watch the sky for around 30 minutes and you may end up seeing a red sprite because these sprites, they are everywhere. They've even been spotted in Malaysia. Okay. These are the red sprite and the tree. Now, this is one of the few cases where I would heavily or I would urge any audience members to check out this APOD page because the writer, Maxime Villard, the explanation here is it's somewhat poetic. He's comparing the sprite to the tree, and if you ever get the chance, I would highly suggest checking out this APOD page. And that brings me to my last image. Let's give this some time to load. This one's not something that was photographed. This is not a real photograph taken, unfortunately. It's an artist's impression of what might be an extremely profound discovery. Methane discovered on distant exoplanets. The credits here are given first off to Ahmad Jabbar Kenji. He was the person who did this beautiful illustration. And then data from NASA, ESA, Canadian Space Agency, and the James Webb Space Telescope. So what's going on here? The beautiful thing about astronomy is that it really connects all the fields. You've got physics, you've got math, you also have chemistry and biology. And I'm going to take you down a little digression to share with you some background information of what made this possible discovery so profound. I'm going to tell you about something called DMS, dimethyl sulfide. These are what give the ocean and the sea its unique scent. If you go out on a fishing trip or anywhere far from shore, as long as you don't smell the shore and you're actually smelling the ocean, smelling the sea, that scent is the result of this dimethyl sulfide, or DMS. Now, DMS is an extremely powerful thing. First off, it travels up to help clouds form and grow so that they reflect more. They keep us cooler. And these DMS, they are the results of phytoplankton. They're from phytoplankton. So whenever we see DMS, we start to wonder about phytoplankton. Now, why are phytoplankton so important, you might ask? Phytoplankton are the basis of the marine food web and affect every single one of our lives. How so? Even though there are 450 times as much plant life on land as there are phytoplankton, these tiny little organisms, they consume 11 billion tons of carbon from the atmosphere every year, which is about as much as all of the plant life combined, from your petite gardens to the grand Amazon rainforest. And from this, they produce more than half of the world's oxygen every year. Phytoplankton. Now, around 2.5 billion years ago, let's talk a little bit about Earth history. If you were to travel 2.5 billion years ago and you went to a beach, what might you see? Well, first of all, you'd have to wear some sort of suit because there is no way you'd survive in that environment. The ocean, what color is the ocean when we look at it now? Well, the water itself is clear, but it seems to reflect the blue from the sky. Back then, the sky was orange. The sea was green. Now, all that changed when cyanobacteria evolved in large quantities and produced great amounts of oxygen. These turned our skies and seas blue. This is something that we call the Great Oxidation Event. But then some 2 billion years later, phytoplankton did the same thing. They made the plant capable of the life we have today. More recently, however, if we were to go to, say, 8 million years ago, the volcanic activity on Earth made the oceans rather unsustainable. There would be pH levels going rampant across the ocean. It would go up and down, and that was not suitable for truly complex life. Now, what happened? Well, some of these phytoplankton, they evolved. They became capable of forming shells of calcium carbonate. And over time, it filled the ocean floor. What happens with this calcium carbonate? Well, these shells, they stay intact at neutral pH levels. Once the pH levels go up, they dissolve into the water. What happens when they dissolve into the water? They chemically interact with the water and neutralize the pH level. These shells created a system that blocked the acidic leakage that we had and made life such as us possible. Now let's talk a little bit more pertaining to the image. So we've talked about DMS, we've talked about phytoplankton. The main thing to remember from all that is DMS is very important. You see DMS, you get a little jittery, you get a little excited. Back in 2015, the Kepler Space Telescope discovered a planet, K218b. It's part of the K218 solar sun system, and that is the star that we see right here. This red dwarf is K218. This planet is meant to be K218b, with this being a little moon. Now, in 2019, the Hubble Space Telescope observed what seemed to be water vapor. And we came to the conclusion that, temperature aside, the atmosphere was very much similar to the gas giants of Uranus and Neptune. Then came this year, 2023. What happened? The James Webb Space Telescope detected carbon dioxide and methane. Now, it does this using the astronomical spectroscopy that some may be familiar with. But basically, it looks at the light coming out of the planet. So the light from the star is going to be influenced in some ways, going to be affected in some ways by the atmosphere. And once we read that, we have an idea of what types of chemicals are in the atmosphere. As I said, carbon dioxide and sulfur. In addition, there were signs that there could be DMS. There could actually be dimethyl sulfide on this planet. It may be, again, may. We still have to confirm it. There's still a lot of work to be done. But it may not only be a habitable planet, but it may actually have life. So stay tuned to the APOD, subscribe to our YouTube channel, because who knows, maybe in our next image, we'll be talking about photographs of aliens from K218b. Thank you.
Yeah, great. We can what they call connect with the aliens, Ryan.
Absolutely.
One of the mankind's deepest calling in existence is to see whether we are alone or not alone in the universe.
And perhaps we are not.
Yeah.
Okay, I will unshare my screen. Let's stop presenting. Okay.
So Bunwei, you have the floor.
Okay, thank you. Let me share my screen first. Can you see my screen now?
Can see your screen? Can you make the text a bit bigger?
Yeah, sure. Okay, so my first presentation on the APOD is on Malaysia Day, 16th of September. Yeah, so wow, this is a very nice. Let me zoom out a little.
Bigger screen.
Yeah, you can see the whole picture here. Okay, so this picture is taken by Jennifer Franklin in Iceland. This is taken in just the south of the Arctic Circle in Iceland. Yeah, so the Arctic Circle is actually a site that consisting many stone arch and then statues. Like it's arranging like a huge sundial, aiming to capture the sun rays, cast the shadows in the precise location, and also to capture the light between the aligned gateway. So go to this picture. This is the picture taken on September 12. So you can see the background. Yeah, is a aurora and it's a aurora northern light. We have we will see many aurora recently is because our solar activity is strong now. Then yeah, so the foreground is the zone of the Arctic Hedge pointing to the sky, and this is a exciting fireball meteor. Yeah, so actually this picture got sound.
Yeah,
this you can see this is the trail that left over by the meteor, and yeah, these were very lucky that captured by a group of aurora hunters. Let me go to the video because yeah, you can see they are actually leaving soon, and then they capture this in a video. Yeah, let me show the full screen maybe. Yeah, so they are actually ready to pack. Yeah, but the scenery is so nice. Can you see?
Yes, you can see them walking.
Yeah.
There you are.
Wow, so bright. So bright for the meteor. It's like
fireball.
Yeah, fireball. And then it's so much light, like a bright sky already. Yeah. Then leaving the trail here. So exciting moment. Yeah. So the trail is like taking like 60 or 90 degree along with the aurora glow. So wow. So lucky.
Beautiful.
Yeah, very beautiful. Okay, so let me go back. Okay, yeah. So this is the fireball over the Iceland. Taking on the September 12th. Okay, so let me go to the next picture. Yep. Okay, next picture. This is picture taken on actually it's also 12th of September, but this is 15th September APOD. So this is the view taken from the flight. You can see this is the flight. So what is inside this picture is can see over the caption here is a Venus, Moon, and the Smoking Mountain. Yeah. Image credit to Luis Miguel. Okay. So he's taking the flight to Mexico, city of Mexico. Can From the view, he saw that the this is a pre-dawn sky before the sunrise. Then can see this is a Venus. Yeah, and then this is a crescent moon. Yeah, the brightness is like almost very bright in the Venus. Yep. So over here, you can see this is eastern horizon is yeah, before the sunrise. So the orange this color. Then this is the smoking mountain. Is a active volcano in Mexico called Popocatépetl. Yeah,
Wow.
this is the name. Okay. All right. So Venus, actually now you can see in the morning now, yeah, is coming to the pre-dawn sky now, and there are several Venus observation in the coming month, which is on 10th of October. Is Venus is going to have a conjunction with Regulus, the brightest object in constellation Leo, when the Regulus is going to rise at 4 a.m. something. Yep. Then on 24th of October, so Venus is going to have its greatest elongation at 7 a.m. Yep. Okay. So this is the picture.
Yes.
Yeah, very nice picture taken from
Beautiful. Yeah.
flight. I always wish to have a flight photo like on the sun when the sun is rise, then sitting beside the window. Yep. Okay, so let me go to my next APOD. Okay, so my next APOD is on the 10th of September. So can see here the capture is
Yes.
an annihilation solar eclipse over the New Mexico.
Yes.
Wow. Okay,
Oh,
so
nice.
this is a ring of fire.
Yeah, yeah, yeah.
Yeah, it's similar as what show in the video show my daughter Chong just now. So yeah, this is not a moon. This is an annular solar eclipse taken by Colin Pinsky. In 2012 sunset time in May of 20th at 7:36 p.m. at their local time from a park near Albuquerque City in New Mexico. Yeah, so you can see this. This is the annular solar eclipse. So because of the moon is too far from the earth to block the entire sun, so you can see the sun is still peeking out over the moon disk, yeah, in a ring of fire. So to capture this picture, actually Colin is drove from Arizona to New Mexico. Then after setting up, is at the right moment, the someone is walked into his shot. Then he never know who is this, but from this picture, this guy probably is also taking maybe his big telescope like telezoom telescope or the camera uh wanting to capture the solar eclipse too. So actually there's a reminder in the caption here, is on the next month 14th of October, across the North and South America, it will have a similar annular solar eclipse come again. Yeah, so it's roughly like 11 years after the 20 May 2012. So it's actually a same type of the solar eclipse, like crossing the similar region. So the greatest point the point of greatest eclipse, like can see this ring of fire is lasting for 5 minutes.
Wow. Oh, you.
Yeah.
So
And
Jom, Boonway, let's go to USA next month.
yeah, let's go.
Quick, book.
Yeah,
book.
most of the eclipse I checked from the list here is almost in the US.
Yeah.
It's not here we totally cannot see.
Yeah.
I think in in Malaysia is like I seeing like wow very long already. Like
Yes.
in Asia is like 2034 or something already.
Yeah.
Yeah, this is very nice, so nice.
Fantastic.
Okay, so and this is my last picture this month. So I pass mic to Dr. Chong.
Yeah. So Dr. Jivaraj, okay, you have the floor.
Yeah, Dr. Jiva.
Yeah.
Okay, can you hear me?
Sure, Dr. Jiva, please. Yeah.
Okay, you'll have to excuse me. I've been looking at the wrong set of lists.
It's okay.
Anyway, I hope, okay. My first slide is the one on this one.
Yeah.
The
19th of September. Yeah.
yes, that's right. I'm going to share this.
Please. Yeah.
How do that now? Have you all got it? Not yet.
Try again. Yeah.
Share.
Maybe Boonway, you can tell Dr. Jivaraj.
Yeah, how do I get about it?
Below there, there's a square box with the arrow pointing up. That's a square.
Yeah, you can see
Okay, got
send now.
That's the one.
Right.
The box with the arrow. Yeah. Share screen button. Yeah.
Okay, got it. Thank you.
Yeah, good. Wonderful. Can see.
All right. Okay, so now this was a surprise about 5 minutes ago, but generally it shows jets from a forming star, or rather protostar. Yeah. Okay. Now it's very nice, very stunning picture actually. Now the question was, do stars always create jets as they form? Not too sure, but as the gravitational cloud of hydrogen and helium gases contract, they start spinning into an accretion disk first. They don't really coalesce into a round sphere just like that. They go into a spinning disk, which then slowly spins faster and faster, and then starts to accrete to a center mass. Now, if they spin at the speeds that they go, it's sometimes too fast and they disintegrate. So in order to maintain the gravitational pull, they have to lose energy. This rotational energy has to be lost. And from what I understand is they lose it by radiating masses and electromagnetic energy, as well as masses through their polar poles on opposite sides. Now you can see one example here. So it spins this way actually at right angles to these two jets that go off. All right. And where the jet interacts with, because it occurs in star nurseries where there are clouds of helium and hydrogen, where they interact with the cloud that's there, they create ionized gases and hot spots. And these are the HH objects. All right. At the same time, the material could be also from here, which is moving at a slower speed compared to the jets. And these can also be ionized to produce these hotspots. Basically, they are taken in various spectrum, in infrared, and also, how shall I say? Yeah, they're able to do spectral analysis of the two jets, which also give an idea of the speed at which they're going. Right? Sorry, I can't tell you much more because it's just been about 2 minutes since I looked at this, and I'm going by what I have.
Good, Dr. Jiva. You're doing well.
Acknowledged then. Okay. Now, there are also other, if you look at it, there are also stars or other solar objects, which stellar objects which give off jets. For example, the binary stars, as they orbit and they start to accrete, they also give off jets at their polar poles. But in this particular form, where the HH1 jets or Herbig Haro objects, they are specifically associated with protostars. That means newly forming protostars, and therefore they are also found very commonly in emission nebulas, dark nebulas. Wherever stars are being formed, you will have HH objects. All right, so I think that's about the most of what I can tell you on this. My next one is also a surprise to me, and that is
September 7th.
September 7th.
Yes.
Aha.
Wow, nicer.
Yes, beautiful picture, isn't it? Really great. Now, this is the large Magellanic Clouds, our nearest satellite galaxies, and best seen in the southern hemisphere, right? It's something akin to a barge spiral. So you're not too sure whether it's ripped up, or shall I say a broken down satellite galaxy due to tidal forces from the Milky Way and the smaller Magellanic Clouds. It was described by Ferdinand Magellan when he circumnavigated the world, and that's where it gets its name from. I can't say much about it since I'm not too the same, but I do remember seeing this when I went to New Zealand, and it was wonderful. I just stumbled on this observatory that was going on. They were having star party tours, and we went in, and they were kind enough to show us all this stuff, and it was really, really stunning. All right, the next one would be the let me see now, that would be
the 1st of September.
Yes, the 1st of September. All right, the 1st of September. Okay, now this one. You see that? Let me see now. Wait, let me present it again. Okay, now this is a wonderful picture. Incredible, really, really incredible. The great globular cluster in Hercules.
Wow.
Yeah, fantastic, isn't it? Really, really, really fantastic. Now, it was initially discovered, or rather described by Edmund Halley, the guy who's famous enough to be mentioned every 76 years, who discovered Halley's Comet. And see now. All right. Okay. Now, basically, if you look at it, let me see now. Can I quickly share something else?
Yes, can see.
Okay. Now, if you look at it, it just looks like a snow globe with all these flakes of light, shimmering light, all in a globular structure, and it's one of the brightest star clusters visible from the northern hemisphere, right? And basically, it was discovered, as I said earlier, by Edmund Halley, and he described it as just a slight patch a bit of maybe something like cotton wool that you may see just faintly with your naked eye. Right, the sky is good and there's no moon. And then, of course, came along Charles Messier, whom we all know about. And he was actually looking for objects which he didn't want. He didn't want all this other stuff. He wanted comets. And he was looking for non-comet-like objects so that he made a list so that he wouldn't get them confused with the comets. And he described it as, with his telescope at that time, which was not powerful enough to resolve it, as just a cloud of light, brighter towards the center, dimmer at the edges, and he described it as a nebula, which he was sure doesn't contain any stars. It wasn't until much later when William Herschel, now he was the guy who actually managed to resolve some of the stars and then coined the phrase the globular cluster. Right? And it's easy to spot it. Of course, nowadays, those days I used to star hop to it from the constellation Hercules, and then you got to go from Vega and look for that keystone structure in the constellation constellation Hercules, and you'll see that M13 is somewhere along the upper border. And nowadays, of course, you don't have to go to all that. Just get a go-to scope, and you'll be able to get M13 very, very clearly. Now, it contains about 100,000 stars, and at a distance of 25,000 light years from us. And it's really packed so tightly across the distance of just 150 light years. So you can imagine the density at the core of this cluster of stars is immense. And I can't even imagine the gravitational forces that are at work keeping this whole thing together. Whether the stars are rotating around each other, around a common center, or whether it's just random movement and they collide here and there. Now, the evolution of globular clusters is a bit, initially they were thought to be quite straightforward. They formed from clouds of gas, the initial primordial gas which was present right from the beginning when the galaxies were formed. And while the stars formed into galaxies, some of these gases formed into stars which didn't join in the formation of the galaxy, but remained as globular clusters in a halo surrounding the galaxy. Now, why do they say that their primordial gases are very young stars? Is because they are quite poor in metallic elements. Now, metallic to an astronomer means anything more than helium. All right, so metallic substances only form when stars age, mature, blow up, seed the cosmos, and then form. You get all these elements being formed. But these stars are just these globular clusters just only have helium and hydrogen, and so they say it must be at least as old as the cosmos itself. But at the same time, there's a few other talking points about this, because although you'll find that they are full of old red giants, there are still quite a number of blue stars, blue stragglers, and they can't account for this. One is, of course, you can say that the red giants fuse into each other and they seed cause nowhere, seed the cosmos, and they form blue young stars. But that's one point which nobody seems to know. So you could say that the formation of these globular clusters is still up for grabs. Now, a point to this thing would be all right, there's an interesting footnote. M13 has been such a prominent astronomical figure that it's iconic. You either see M13, you see Nebula, you see the Pleiades. And as an interesting footnote is in 1974, two of quite famous astronomers, Carl Sagan and Frank Drake, and their team sent a radio message from the Arecibo radio telescope to the globular cluster to M13.
Wow.
Yeah, and it's a very I'm not able to share the presentation slide with this. I'm not sure how to do that, but it's a very nice graphic of the message that they sent. Basically binary code encoding the DNA, the numbers 1 to 10, hydrogen, the elements or atoms for hydrogen and carbon and so on. But it was sent in 1974, and considering the fact it's going to take another 250,000 years to go there, I think, rather 25,000 years to go there, I think it'd be quite difficult to wait for a reply. Now, at the same time, anyway, astronomers also decided that there's not going to be much life within a globular cluster because of the lack of minerals or metallic elements. You won't have much planetary rocky planets being formed. You won't have a basis for intelligent life to form. So probably there is just a message into space being sent. Now, personally, I feel that M31 is a bit of undue importance. Given to it as a fabulous globular cluster, because when I saw my first globular cluster, it was Omega Centauri.
Wow, that's even more fantastic.
Yes, and Omega Centauri is out of this world.
Yeah.
Look at pictures comparing M13 and Omega Centauri. It's no fight.
Yeah.
Omega Centauri is just fantastic, really unbelievable. So I always felt M13 was okay, but the amount of importance it was given in the thing, okay, not too bad, but give me Omega Centauri anytime.
Yeah.
Recently, just as a personal note, I've got a smart telescope. I've imaged both M13 and Omega Centauri, and the pictures are wonderful. Really, really wonderful.
It was a Vespera telescope, Dr. Jiva, you forgot to mention.
Yeah, those scopes. And the images, even though with a small 2-inch diameter scope, is fantastic.
And I was next to Dr. Jiva, and he imaged some of those objects in Malaysia. Yeah.
But I think almost all of us have seen this globular.
Incredible. It's actually a revolution in observational astronomy for amateur astronomers. Yeah.
So, apologies again for having the wrong slides and the thing, but next time I'll probably do a better job.
Well presented, Dr. Jivaraj.
Thank you.
Right, huh? Okay. So I'll share my screen. Okay. Yeah. Thank you. September 17th. Another total solar eclipse. All right. So basically, I'll read out the acknowledgements here. So by our Wang Leitian, an amateur astronomer from China. So at that time, he was in a place called Xiamen. So Xiamen is on the side of South China in Fujian province. So basically, he took the total solar eclipse like that. But hey, what's this on the left and the right? So there's a trick there. So when the moon is able to cover the sun completely, so you have to remember the first contact, second contact, third contact, fourth contact. And let's say on the left is when the moon is first cover the sun completely. You find that here, this part is where the moon is able to cover the sun completely. All right. And here also cover completely. But over here, you have, in other words, there's mountains on the moon here. You saw the bump here? There's a bump here. You create these two big objects here. So basically, these mountains on the moon are reversed. All right. By right, they should be poking out from here. But they reverse it so that instead of going from left to right, they're going from right to left. The mountains of the moon. And here you have the so-called light passing through the lunar valleys, or what we call the Baily's Beats. During the total eclipse, you have the Baily's Beats. So here, the moon covers the sun completely. Here, Baily's Beat. And on the other side, when the moon uncovers the sun, again, you have the Baily's Beats, and then you have the mountain. But they reverse it. So you take it from, you must take many multiple shots, especially at the part where you cover the sun completely, and later on, when it uncovers the sun, then you're able to exaggerate this. So basically, the heights of the mountains on the moon are exaggerated in the western part of the moon and the eastern part, but not on the northern and the southern part. So beautiful. And basically, I find why I like this airport very nicely. You never know. Somehow or other, some of the astronomers, amateur astronomers, they come up with new techniques. Of course, this is quite an old technique. But sometimes somebody come up with a very new technique which nobody can imagine, but very imaginative. Okay, the total solar eclipse, all right, in China, all right, what they call in 2020, all right. This is the one by Wang Leiqian from Xiamen in China. The next airport would be 13th of September. Okay, I give the acknowledgement first here, below here. It's by giant English and astronomer in the University of Manitoba. So University of Manitoba is in the city of Winnipeg in Canada, very cool place. And then you have Nathan Deck, an astronomer in Queen's University. Queen's University is in Ontario in Canada. And Wallaby Survey. Wallaby Survey is a famous array of radio telescope in Western Australia. Radio telescope, right? In the ASCAP, SKA array. And you have the India lab, also BC lab. And this is the CIRO, Commonwealth Scientific Industrial Research Organization of Australia, ASCAP. And you have a famous NAOJ, National Astronomical Observatory of Japan, Subaru. Remember, the Japanese are very proud that they have their big Subaru telescope, a single mirror optical telescope of 8.2 meters next to Keck telescope in Mauna Kea Mountain in Hawaii. Okay, the text, of course, is by giant English from the University of Manitoba. So basically, you have a weird thing. So I will make it smaller now. So you have here the central part is taken by optical telescope. The telescope which we shown earlier. All right, optical telescope, and then here this polar ring means this, of course, the disk of the galaxy. Imagine it is at the equatorial region, but this is over the polar region. It's taken by radio telescope. Because I also showed below there, some of them are radio telescope. For example, the radio telescope Wallaby in Western Australia, and then you can see it. So they were trying to find out what actually caused it. So here there are two possibilities. One is that you have galaxies in collision, and one of this central galaxy will what is called distort the other galaxy, and then you pull the string of the stars in the second galaxy to form a kind of polar, orbiting in the polar orbit around the galaxy. And they were able to observe it in radio waves. So basically, there are a lot of hydrogen here. Okay, so this is radio optical astronomy and radio astronomy. Okay, and then there are more information here. Okay, this is our NGC 4632. Now, NGC means New General Catalog. Actually, there's nothing new about it, more than 100 years old. But the name has stuck with us. So, NGC 4632, New General Catalog. Remember, we have all kinds of catalog in astronomy. Messier Catalog, 110 objects. And then you have the New General Catalog, thousands of objects. You have the IC, Index Catalog, thousands of objects. And you have our Caldwell Catalog. Remember Caldwell? Patrick Moore? Or Sir Patrick Moore, his catalog also got, all right, Caldwell catalog. So this is the polar ring, what they call galaxy with a hidden polar ring. Hidden meaning in the sense that in radio wave. So you observe it in optical telescope, you don't see it. Only you observe in the optical telescope, the center galaxy will appear, and you observe also in with a second radio telescope, you will see it. Okay, that's why it makes it so interesting. So next picture should be 12th of September. So I will read out the acknowledgement first. Okay. So you have NASA here, which is we know, and the ESA, European Space Agency, and then you have the Jennifer Ross and the HFF team. So basically, this is a team in the Hubble Space Telescope. Of course, SCSCI is a famous institute, science telescope, Space Telescope, Science Institute in Johns Hopkins University near Baltimore. Baltimore is near to Washington, D.C. So SCSCI is the one that runs the Hubble telescope. And now SCSCI also runs the James Webb Space Telescope. So now we are going to talk more of, previously for 20 years it was Hubble. Now it will be Webb. Okay. So this is the Hubble Space Telescope. Why you see the central star here has 4 spikes? Because the strut that holds the primary mirror of Hubble has 4 struts. That's why you have this what they call 6 spikes. Earlier, a picture by Dr. Jiva, that's a star has 6 big spikes and 2 small spikes, 8 spikes. That shows that it's James Webb. James Webb, we have 6 spikes, but Hubble has 4 spikes. But what makes it beautiful is, hey, all these are galaxies, not stars, except for this star here and this star here. But most of them are galaxies millions of light years away, even further. So basically, this is a cosmological picture. Cosmological means dealing with the universe as a whole. So these are universe at the edge of the universe from the Earth, meaning billions of light years from the Earth. Every single one is a galaxy. The interesting one is not a galaxy. We have taken a lot of optical pictures with galaxies, thousands of galaxies, but these lines here, that's what makes it strange. The lines, and that is bright line here. So these are the instances of the famous gravitational lensing that was predicted by Albert Einstein with his general theory of relativity and was first seen only in the 1980s. I remember I was following the news in the Sky and Telescope in the 1980s, and the first confirmation of a gravitational lens. So exciting, Of course, the first confirmation of a gravitational lens is not of the galaxy, but of the starlight bent by the sun during the 1919 total solar eclipse. That was the first confirmation of light being bent by gravity. Light from the star, background star, bent by the sun's gravity. But this is different. This is the foreground galaxy, and far behind there are many, many galaxies. And as the galaxies come closer to the Earth, they pass over the foreground galaxy, they have strong gravity, and the strong gravity of the foreground galaxy will bend the light into, I would say, a weird pattern. So imagine that you have a lot of stars. Let's say, imagine you're on the Earth's surface, far away, a lot of people shining torchlight, and between the people with the torchlight and you, there are a lot of lenses. So as the light passes through all these lenses, you create weird pattern. So that's why this is a weird pattern, All right. And don't think that, for example, this one, we call it a kind of dragon arc. Okay, what makes that? Somewhere far behind, there are a lot of bright galaxies, and as the light from the bright galaxy come to us, there's a galaxy in the foreground which you don't see well, dark, but a lot of mass, and they bend the light. But the beautiful part of gravitational lensing, being based on the 1915 general theory of relativity proposed by Einstein, is weird. It doesn't mean that the light you see here and the light you see here, the light you see all along this thread came from the background galaxy at the same time. No, because the light from the background galaxy, as it passes through and bent by the foreground galaxy and reaches you to produce this image here, takes a different path. And then on the light from the background galaxy to pass through the pass by the foreground galaxy to reach here, it's a different path. So maybe the light here is younger. The light here, as you go to the right, the light that goes to the right is take a longer time to travel. So basically, you're looking here at a time machine. So this is what you see, the light from the galaxy, let's say now, but this was the light from the galaxy a year ago, 10 years ago, 100 years ago, 5 years ago, a million years ago, all at the same stretch, you see light. So imagine, I will used to give a talk, imagine somewhere in the background galaxy, there's an alien, and the light from the alien comes to closer to the Earth and is bent by the in-between galaxy, and we see you can see the alien when the alien is 1 year old, 2 year old, 100 years old. Imagine the alien can live to 500 years old. You can see the alien, the whole history of the alien is now shown here, all in one image. That's the weirdness of gravitational lensing and all kinds of lensing. All right, and of course they have seen so many instances. They predicted the Einstein cross. They saw it, confirmed. They predicted the Einstein ring. They saw it, confirmed. So this is the case of gravitational lensing, and it's named after our famous American astronomer George Ogden Abel, and this is Abel 370 and beyond. Just very fantastic. This is weird, So basically, this shows the extreme curvature of space and time together as the light from the background galaxy come towards to Earth, and because there's a strong gravity there, not gravity because of a neutron star, no, the gravity of a whole galaxy millions of light years of space-time around the galaxies are distorted. So the light from the background galaxies are distorted and reach us. And you see the extreme gravitational lensing there. Of course, very much closer, of course, is this star in our Milky Way. There's no lensing. But those galaxies here are millions of light years, hundreds of millions of light years, billions of light years from Earth. Okay, so this is beautiful, huh? So gravitational lensing in Galaxy Cluster able 370 and beyond. Okay, so the next one is September the 9th. Again, Nishimura. All right, Nishimura. We have this. So Peter Kenneth is an American photographer, and his astronomy photograph and Lenso photograph is very popular. It's actually been put in many of the American embassies around the world. American astrophotographer. And then you see here the comet. All right. And now we know that bye-bye Nishimura. Why? Because 12th of September, closest approach to the Earth. 17th of September, a week ago, perihelion, closer to the sun. So now it's going away from the sun, and what's a period about 400 years. So hope we all can stay healthy here. Wait for another 400 years, it will come back again. But by the way, Dr. Jiva, were you able to observe Halley in 1986, 87?
No.
So we were in USM, our longest observation of any astronomy event was when the club was formed in 1986. Halley's Comet. We were able to see Halley's Comet from November 1986 to March 1987 for 5 months. Every day at night we came up to observe. So now basically, this Peter Kenneth was able to do it. So basically, you see here, I'll make it smaller. Okay. So now this was taken when? They never say what's the date. Imagine it was taken before perihelion. So basically, you have the sun on the bottom right corner, and the sunlight and the sun's radiation pressure and the solar wind will hit the nucleus of the comet. The nucleus usually is very small. It is a frozen ball of ice and dust and rock. Okay, and it will, because it's in the vacuum, it will sublimate the material, not liquefy. From solid ice become vapor. Sublimation, it will expand to form the coma, and then you have the sunlight keep on falling on it, and the solar wind keep on falling to it, and you have two of the tails. So basically here you have this is the dust tail. All right, this dust tail is caused by the solar wind hitting the evaporated particles from the nucleus to form this thing. All right, the ion tail, the straight tail, and there's also this is the dust tail, the crooked tail, and this is the ion tail formed by the sun's radiation pressure hitting the particles evaporated to form. But this one, the crooked dust tail and this ion tail are not so evident. But some of the other comets, you have two tails, the crooked dust tail and the straight ion tail. But it's beautiful. Why green? Because in the nucleus of the comet, you have, in the ice, you have what's called diatomic carbon. I mean, imagine carbon, normally you have a single atom with 4 valence bond. But this is two carbon atoms attached together to form a diatomic carbon molecule. So basically, it's a molecule of 2 carbons attached to each other with 2 covalent bonds. So basically, we have the electrons orbiting around the carbon, each carbon. So when you have the solar wind particles hit and the UV light hit the electrons in the outer orbit, the electrons will be ejected away from the carbon atom. But once the electrons are ejected, we have an empty electron shell around the carbon atom. So that electron shell must be filled. So the upper electrons or even the outside electrons will fill in the ejected electron, and the moment they fill it, they will give off light. So usually the what they call the electrons, when they are promoted from a lower orbit to a higher orbit, is a higher energy. But when you drop down to a lower energy, it will give off the green light. So this is a case of what is called luminescence. So aurora, Dr. Jiva, is also because of luminescence. So there's a similarity. So imagine you see in green in Iceland, aurora and a comet at the same time. So the green light of the aurora comes with the same phenomena as the green light from the coma of the comet. All right, like this. So this is Nishimura. So Nishimura is already famous now. All right. So we hope that we have in the coming years, we should be able to see some visible, naked eye comets. Over the past 30 years, we have seen quite a few of the bright comets. The most, of course, was 1995, Hyakutake. Imagine Hyakutake. Dr. Jiva, were you able to observe Hyakutake?
Yes.
I always remember this because Dr. Zhang, you mentioned this so many times.
Yeah, sorry, I repeat.
No, I mean like you can see like it's so bright, then we never see, so sad.
There was about 5 crazy nights in the early morning in USM between School of Chemistry and Biology. So many people came and went gaga. With your naked eye, you can see from the coma to the edge of the tail, 1/3 of the sky. And I remember Lim Chun Kiap took a photo, half the sky. And I was in Georgetown in Penang Road. I stuck my head out of the car window and I could see the comet clearly. The problem is that the comet flew by very close to the Earth. That's why it was so bright. And because it's very close to the Earth, it went past the Earth like a roaring train. So within 5 days, from the southern hemisphere, it came to the equator, and not within 5 days, it disappeared. That's a penalty to pay for seeing a bright comet. It's very bright because it passed near the Earth, but because it's near to the Earth, it moves by very fast. So you don't see it for too long. Whereas Halley's Comet and Comet Hale-Bopp, you can see for many, many days, many months, because they're further away. So anyway, Hyakutake was the most fantastic comet, right? We saw, and everyone was unforgettable 5 days in USM. Okay, so Nishimura, so bye-bye Nishimura, see you again 400 years from today. Okay, so now we go to the last picture, September the 3rd, another comet, and we observed this in USM. I don't know whether I mentioned this. What called Bombay? I'll make it larger. Comet Schwarzman-Wachmann 3 fragments. That means there are two guys. One is Schwarzman, one is Wachmann, and these two people, they have found 3 comets. And this is comet number 3. And this is a comet fragment. So basically, what they call, there are many, so basically like this. So you have a comet, which is a nucleus. The nucleus, actually, we cannot see the nucleus, we cannot see. But the nucleus will form a coma, all right? Some of the comets, the coma can be very large, few 100,000 kilometers in diameter. And then at the sunlight and the sun's solar wind keep on colliding with the coma, and you form the tail. So basically, you have here a coma, and basically you have many disconnection events. So you have the smaller lumps of the nuclei broke off, and from this individual nuclei, small one, we have the small coma and the tail also. And this is our comet Schwarzman-Wachmann number 3 with the fragments. Okay, so this they give a nice name. They call it the cosmic souffle. Some of you, they have been to France, so I don't know whether it's served as a dessert or entree. So they will serve you a kind of piece of cake, and looks like a tart, but not a tart. On top is kind of white, what they call kind of creamy, kind of, they call it the souffle, a kind of French cake. So very nice. So this is Comet Schwarzman-Wachmann, and taken by NASA, of course, European Space Agency, ESA, of course, by this scientists working in JSU APM. So JSU, we know, Johns Hopkins University, where you have the SCI Institute, Hubble Space Telescope, James Webb Telescope. Okay, in JSU, you have the APL, the famous Applied Physics Laboratory. So basically, a lot of the equipment and the science is done by the APL, Applied Physics Laboratory in Johns Hopkins University. Okay, next to SCI here. These two are the Mr. and Dr. Mushler and Dr. are working in SCI Science Institute. It's the one that runs Hubble, and of course this this James Webb. So basically, because this was taken years ago, 1995, most likely it's taken by Hubble. It was taken by Hubble. Beautiful, huh? So it's a Comet Schwarzman-Wachmann 3 cosmic souffle. So Dr. Jiva, we have been telling our Penang amateurs, when you take picture, why you want to name some of the pictures after some pictures? Why not name after Malaysian thing? Maybe you see a spiky object you observe. I told our CK, call it the cosmic durian, the cosmic rambutan. No, why not? So we want to promote Malaysia, give it a Malaysian name. KK. So next time you take a nice picture, with Vespera, with C star 50. Give it a nice Malaysian name. Looks like a Malaysian fruit or something, or like this. So like this. So basically, remember, even Comet got many types. So what happened to this one? So because if this is before perihelion already broke up, so when it goes near the sun, it may be a kamikaze, suicide comet. It may be crashed and burned, disappear in the sun. We have seen before. For example, many years ago, you have the SOHO telescope, Solar Observatory, Heliospheric Observatory, and also this SDO, Solar Dynamics Observatory. A lot of the kamikaze comet fall into the sun and burn up. But sometimes it may not, hit the sun. It go around the sun and go away from the solar system again, and you see a comet train. Remember, 1994, Comet Shoemaker Levi number 9 passed by this Jupiter. The gravity of Jupiter broke it into 22 pieces. And some months later, came back and back into Jupiter one by one by one. Dr. Jiva, did you see the event? Okay. Comet Shoemaker Levi number 9 crashed into the Jupiter.
Jupiter.
7 days. It was 7 crazy nights in US.
Black shadows on Jupiter.
Yeah, and all the black eyes on Jupiter.
Yeah.
So, and you saw even just now, I saw, only just now in YouTube, Japanese amateur astronomer also videotaped another comet or some asteroid hit into Jupiter, a flash on Jupiter. But this is 22 times. And there was a fragment A, B, C, D, E, F, G, up to 22 fragments. And I told my US student, fragment G, the nucleus was 1 kilometer large, solid nucleus. I told them that if it were to hit the Earth, fragment G, human being become dinosaur, bye-bye. Yeah. So we are living in very interesting time, okay? But unfortunately, Nishimura didn't move close enough to the sun, so it didn't break up. It will happen for the future comet, right? So this is Comet Swatchman Wachman 3 passing close to the sun. Okay, I think that's all for me. Okay, I go back to the group. Yeah. So Rayan and Wunwei and Michael, any question?
No question on both sides.
No question on both sides, huh? Okay. So very good. So thanks, Andy, for joining us. Don't go yet. So Michael, we can stop. We can have a bit of a chat before we. Okay, yeah, okay. So thank you everyone for following our airport presentation on today, 24th of September, 2023, with our 4 presenters, Mr. Bunwei, Rain Akadri, Dr. Jiva Nadaraja, and myself. All right. So we hope to see you again next month in October. And of course, a lot of things are coming also. All right. Now remember, we are past what they call Autumn Equinox, 21st of September. So in the coming months, a lot of events will be occurring, and we'll be having our Mid-Autumn Festival, Mooncake Festival Stargazing on the 30th of September, next Saturday night in Kapal Singrai at 9 p.m. Kapal Singrai is a kind of promenade on the island of Penang, Georgetown, okay, in Malaysia. Okay, so thank you for watching, everyone.